Okay, UDU substitution with polynomials. Evaluate the following integrals using UDU substitution. Alright, so we basically want to find antiderivative, and this process called UDU substitution is like the chain rule for derivatives, and it allows you to take almost all the other integrals that are out there. Okay, so it's also really tricky for students at first. So what I want to do is pick something that'll make this look like a polynomial so I can use the power rule. So I'm going to let u equal x squared plus 1. And I'm going to take the derivative of that. So I could say du dx is 2x, which means if I view this quotient as a fraction, I could say du equals 2x dx. Okay? And that's normally what's written every time we see a problem like this. We usually write it like that. So, I now see that this part here is u, and this part here is du. So that means I could rewrite the integral as u squared du. Now that I have it u squared du, I can take the antiderivative using the power rule, so I get u cubed over 3 plus a constant integration c, and I could write that 1/3. Now u was really x squared plus 1, so we get x squared plus 1 cubed plus c. Now if you wanted to check that, right, we could take the derivative of that. So if let's try a color that will be visible on screen. So if I took the derivative with respect to x of 1/3 x squared plus 1 cubed plus c, right? Well, the 3 will go to the front by the power rule, so I get 3 times 1/3 x squared plus 1 squared times derivative inside 2x, and derivative of c will be 0. So now the 3's cancel, so I get x squared plus 1 squared times 2x, which is what I started with in the original problem. Okay? So definitely the check worked. Okay, let's go through some other problems. Alright. I'm going to let u equal x squared plus 1. That means so du, when I take the derivative of this, will be 2x dx. Alright, so now, if you look, there's my u, and if I had a 2 here, that would be my du, right? du, 2x dx. But I can put a 2 in there if I put a 1/2 on the outside. So we get a new integral, 1/2 x squared plus 1 cubed 2x dx. And so again, you can see that's my du and that's my u. And I could do that because 1/2 times 2 is 1, and multiplying by 1 doesn't change the value. So now I have 1/2 u cubed du. So when I take the antiderivative, I use the power rule like that. So I get 1/8 x squared plus 1 to the 4th plus c. 1/2, 2 times 4 is 8. And that's the answer to that problem. Okay, let's try a couple more. Okay, number 3. Well, I'm ready to write that as 2x minus 1 to the 1/2 power dx. Okay, because square root is 1/2 power. I'm going to let u be 2x minus 1. So du will be a derivative of that, it would be 2 dx. Well, if I put a 2 there and a 1/2 outside there, 2 times 1/2 is 1. So I'm not changing the value of the integral. So I have 1/2 integral 2x minus 1 to the 1/2 times 2 dx. Well, that's my du, and that's my u. So I get 1/2 u the 1/2 du. So I take the antiderivative. U the 1/2, use the power rule. Add 1, get 3 halves. divide by 3/2 plus c. Well, that's 1/2 times 2/3 u to the 3/2 plus c. So when you divide by a fraction, multiply by the reciprocal. The 2's divide out, because that's 1. So I get 1/3 2x minus 1 to the 3/2 plus c. Okay, and again, this is the analog of the chain rule. So I'm going to rewrite this one as 2x minus 1 to the minus 1/2 dx. I'm going to let u equal 2x minus 1. So du is going to equal 2 dx. To make that happen, I need a 2 there and a 1/2 outside the integral. So I get 1/2 integral of 2x minus 1 to the negative 1/2 times 2 dx. Again, that was my du, and that's my u. So I get 1/2 integral of u to the minus 1/2 du. Now that's a simpler integral I can use the power rule on. So 1/2 u to the 1/2 divided by 1/2 plus c. So a half divided by a half, that's 1. So I get 2x minus 1 to the 1/2 power plus c, or I can write that as a square root of 2x minus 1 plus c. Again, you could check all those by applying, taking a derivative and applying the chain rule.